Hello, everyone. This presentation is for IRPS 2023, and the number of this presentation is 8C.5, and the title of the talk is Thermally Activated Failure Mechanisms of 0.25 micrometer radio frequency AlGaN GaN HEMTs submitted to long-term lab tests. The work was done in University of Padua and supported by the projects listed here. My name is Gao Zhan and Veronica, so we can start now. The purpose of this work is to present a systematic study of thermal and electrothermal degradation of a 0.25 micrometer gate length AlGaN GaN technology. This is the table of contents of this presentation. As we have seen that the objective of this work is to present a systematic study of thermal and electrothermal degradation of a 0.25 micrometer gate length AlGaN GaN technology. It is because that nowadays GaN-based HEMTs have been adopted for electric mobility, radar, 5G communication systems, airspace applications, and so on. However, the device reliabilities and the failure mechanisms of the devices during operations are still to be studied in depth. Therefore, this work is conducted. The devices used in this work are based on AlGaN GaN heterostructures grown on silicon carbide substrate using a 0.25 micrometer gate length, a standard process. In order to reduce the short channel effects and substrate leakage current, the GaN buffer is doped with iron. The ohmic contact is defined using titanium, aluminum, nickel, and gold metal stack, and the gate is T-shaped gate defined using platinum, nickel, and gold. Silicon nitride was used as surface passivation and dielectric layer underneath the source-connected field plate. Firstly, some preliminary characterizations were done on the devices. Then the devices were submitted to two kinds of long-term tests: thermal storage test and the high temperature operating lab test. Both were done in air condition. For the thermal storage test, the devices were on wafer devices were mm, mm, were kept in both in ovens at 275 degree, 300 degree, and 325 degree without any bias. And for high temperature operating lab test, the tests were done on packaged devices at a fixed bias condition with a fixed drain current of 100 milliamp per millimeter and a fixed drain voltage of 30 volts at three junction temperatures 210, 225, and 250 degrees. Afterwards, some devices were selected for focused on beam cross-sectioning and scanning transmission, electron microscopy, and analysis in order to understand the origins of the degradations. For the thermal storage test, a piece of wafer was cut into quarters. One quarter was kept as a reference, and the other three quarters were used for thermal storage tests in air at three temperatures shown here for duration of 2000 hours. For each temperature, during the storage test, the pieces were taken out of from the oven and cooled down to room temperature for DC characterization at interim measurement time. Various device layouts on the wafer were tested, including HEMTs with a gate length of 100 micrometer with and without cells connected field plate, 400 micron, 750 micron gate width with a self-connected field plate. For the high temperature operating test, the test was done using an XLIF test system. On packaged devices, um, dynamic evaluation circuit using a 10-finger AlGaN GaN HEMTs from the same wafer design of the previous storage test were mounted by breathing into ceramic short packages. The quality of the die attached was evaluated using X-ray microradiography on each tested devices. Thermal resistance were evaluated using the method described in this reference. During test, the devices were biased at 100 milliampere per millimeter drain current and 30 volts of drain voltage at the three junction temperatures for 2000 hours. From the preliminary small signal as parameter characterization, the maximum frequency of the device is around like 42 gigahertz, and the cutoff frequency is around 18 gigahertz, as shown here. For the thermal storage test, from the electrical characterization, a gradual drain current decrease and transconductance decrease is observed in all the device in all kinds of devices. And non-monotonic leakage current change and threshold voltage shift are observed regardless of device layout, as can be seen here. If considering 10% drain current decrease as a failure criteria, the time to failure can be extracted from the three temperatures. Fitting the time to failure using an harness temperature accelerated lifetime model, the activation energy is around 1.8 electrovolts. And the time to failure at 200-degree junction temperature is predicted to be over 200 years. From the contact resistance and heat resistance measurements using the transmission line method on the structures, on the test structures with and without gate metal contact. For the test structures without gate metal contact increase less than 10% uh, in contact resistance and sheet resistance are observed. Well, for the structures with gate metal contact, more than 275 percentage sheet resistance increase is observed. And observing from the IV characteristics of the Schottky gate contact, a non-monotonic Schottky barrier height change is observed. Within the first few hours storage, the Schottky barrier height increases. With the storage goes on, the Schottky barrier height started to decrease, and until the end of the storage test. This has been observed in a previous publication in AlGaN GaN HEMTs adopting nickel platinum gold gate metallization. From the dark field STM image and the index uh, composition profile, it is observed that there's nickel platinum alloy and nickel gold alloys formed at the gate contact and the gate semi-epi interface. The mixed metal semiconductor interface leads to the non-monotonic short barrier height change and the two-deck density decrease. In the meanwhile, vertical cracks are observed at the gate corner of the device, which could be due to the different thermal expansion coefficient of gallium nitride, argon, and silicon nitride. Summarizing the results from the thermal storage test from the electrical characterization, a non-uniform Schottky barrier height change, a joint current and transconductance decrease are observed, and resistance increase are observed. And the activation energy from the time to failure estimation is around 1.8 electrovolts. From the FIB-STM analysis, metallic interdiffusion at the gate epi-layer interface are observed, and vertical cracks are observed at the gate corners. The degradation mechanism can be due to thermomechanical effects. For the high temperature operating life tests, from the electrical characterization, joint current decrease, transconductance decrease are observed, as well as positivity shift and leakage current increase. As shown here, considering 20% joint current decrease as a failure criteria, the time to failure are fitted with an activation energy of around 1.0 electrovolts, and the estimated time to failure at 200 degrees is more than 15.6 years. The different activation energy indicates a different failure mechanism compared with the storage test. The bright field STM images of the devices showed that the cracks, pits and cracks at the gate corner on the towards the drain side. And the oxygen index map showed that the oxygen at the platinum AlGaN interface and in the pits extended into the AlGaN barrier and the GaN buffer. The degradation can be explained by that oxygen at the gate edge migrates along the gate edge, oxidized the AlGaN surface and penetrated into the GaN layer. And it can be explained by electrochemical oxidation effects. Summarizing the high temperature operating life test from the electrical characterization, drain current decrease on resistance increase and positivity shift and leakage current increase are observed. The activation energy is around 1.0 electrovolts. Pits and cracks are observed at the gate edge towards the drain side from the STM images. And the degradation can be explained by the electrochemical oxidation effects. In summary, in this work, two kinds of long-term tests were done on 0.25 micrometer gate length AlGaN GaN technology. From the thermal storage test, the activation energy is around 1.8 electrovolts. Due to thermal mechanical effects and metallic interdiffusion at the gate contact and the gate contact epilayer interface are observed, and the cracks are observed at the gate corner from the STEM analysis. For the HTOL test, the activation energy is around 1.0 electrovolts, and the degradation can be due to electrochemical oxidation effects. Pits and cracks at the gate edge towards the drain sides are observed, and oxygen are observed in the pits and cracks. This work shows that optimizing the gate metal deposition and growth processes and redesign the gate metal contact scheme can greatly improve the reliability and lifetime of AlGaN GaN HEMTs at high temperature operations. Thank you very much for your attention. And if you have further questions, please, you are free to contact me here. Many thanks again. Bye bye.